Glad to have everyone here for week two of our biostatistics intensive summer workshop. It's great to have everybody here. For today, we are going to move from the week one foundations folder to the week two statistical modeling folder. And we can see we have days 6 through 9 here, that all the materials are in there. Today, we're going to be using the linear regression materials. Um, and so you could open those up. We have some slides in here, and we have an example that we're going to go over. So if any of those, if any of you do not have this stuff downloaded, please just note that in the chat. And I know Elena and Yanan, who are helping us out here, will be able to help you out and get you started with where to go to find all the materials and everything. But for now, you can open up the slides, double click on those, and also open up the file that says day 6 linear regression, not the one that has the PM lab on it, just the day 6 linear regression part. And we're going to use this as we go over. It's going to use the Framingham data, which we used a lot in week one. We're going to continue on with that. Okay, great. All right, so linear regression. This is what we're going to start with this week with our statistical modeling section. So linear regression is something that is very common, still very common today. It's been around for, I think, about 150 years. So it's a very old procedure, but is still extremely, extremely useful. It was invented in the 1880s by a statistician with the last name Galton. He was looking at his question was, seems kind of silly today, but his question was, do taller parents? So he got data of parents' heights and the heights of their adult children, and he plotted them on a curve to see if there was some relationship between those two. Of course, there was. Taller parents tend to have taller children. But what he noticed was that very tall parents, like the tallest of the tall parents, their kids tended to be shorter than they were. And conversely, very short parents, the parents that were the lowest on the curve, their kids tended to be taller than they were. And he called this regression towards mediocrity. Nowadays, you hear the phrase regression towards the mean, and that is where the term regression comes from. So linear regression comes from that initial term, regression towards mediocrity. And boom, we're still using the term regression here today. Go through quick outline of what we'll be doing here today. We'll start with simple linear regression, which is when we just have one predictor variable, how to estimate that, how to make some inferences. We'll go to multiple linear regression and model diagnostics, and then we'll talk about inferences on the multiple linear regression model. This is a little humorous figure here, some of the curve fitting methods, what they say. I encourage you to look over that. So a linear regression model, what we're going to be doing here is we are going to use this to relate two variables to one another. So we have two variables and we're interested in their covariation, how they are related to one another. Are they related to one another? As I said, these are very old methods. They predate computers, but they're still among the most widely used tools in applied statistics. And even in new statistical methods, a lot of the stuff that I do I do a lot in high dimensional linear regression. A lot of it just boils down to simple linear regression. Some of the stuff that we'll be doing here today, they're still very powerful methods. Great thing about them, nice interpretation to linear regression. They tell us some really useful information about how variables are related to one another. It's a very simple relationship because it's linear, but it's still very useful as an approximation for many of the relationships that we see. There are two uses of a linear regression model. Okay, so when you're saying, do I want to use a linear regression model? There are two uses. First one, explanation. So we want to estimate the relationship between a particular variable and an outcome. So for example, we want to estimate the relationship between age and systolic blood pressure. That's what we're interested in. Okay, it's more the explanation type analysis. That's the style. That's what we use linear regression more for in public health. So I would say 19 times out of 20, when we're in public health and we're running a linear regression model, that's the type of model that we are running. So we're interested in how two variables are related to one another. Are two variables related to one another? So that all goes under that first bullet, that explanation bullet. The second one is for prediction. So we have some outcomes, we have predictors of this outcome, and what we want to do, we're not interested in any one particular predictor. We're just interested in using that group of predictors to tell us what likely values of the outcome are. So this is the more prediction side of things. That is not as common, not as common in public health, but maybe in your field, that's more what it's used for. We'll talk about the assumptions of these models. So for our inferences, for our estimates to be correct, we have to have certain assumptions. We'll talk about how to check those, what are the assumptions, and how do we implement those in R, of course. We'll start with simple linear regression. So the most important thing is that first off, we have a continuous outcome. So we have some numerical outcome that is continuous, or at least close enough to continuous. So, systolic blood pressure, BMI, some measure of diet that is continuous. We're not talking about an outcome that's a 0 or a 1, or a 0, 1, or a 2, or even a 0, 1, 2 up to 10. Even something like that, we probably wouldn't want to use linear regression for, but people do. So we have some numerical outcome, some continuous outcome, and we have some predictor variables. The outcome, we could also call it the dependent variable, the predictor variables. I will usually call them the predictors or the covariates. People also call them independent variables. Features is another term. You'll hear that term more in the machine learning literature, but I'll usually go with predictor variables or just covariates. So we call this a linear regression outcome because of the coefficients, not because of the predictors. So the predictors, we can have nonlinear terms, but in terms of the coefficients, it's always going to be linear. So we'll explain that when we talk about some of the nonlinear models we have. So simple linear regression, which we'll talk about first, that's when we just have one predictor variable. So it starts off very simple. So you see here the statistical model for a simple linear regression. We have two parameters there. We have beta 0, we have beta 1. Y is our outcome, X is our predictor, and then we have the Greek letter epsilon, which is our error term. The definition of beta 0, that's going to be the predicted value of Y when X is equal to 0. So when X is equal to 0, we won't have this term in our model, just have beta 0 in the error term. So beta 0 is going to be our expected value when X is equal to 0. This may not be meaningful at all. So the first model we're going to run is age and systolic blood pressure. So beta 0 is the predicted systolic blood pressure when you have an age of 0. Beta 0 is that, excuse me. So that it's not really meaningful is the point. Beta 1 is going to be the slope. This is you are more interested in, and that's going to be the expected change in y for a 1 unit increase in x. And then epsilon here, this is just random error. It's the piece of y that we can't explain using our variable x. There are some assumptions on independence that we'll talk about. So I wanted to show you this figure first, and we'll go back to the assumptions after this. So you see here what the statistical model looks like graphically. We have our x variable, we have our y variable. That line is going to be the overall linear relationship between x and y. Now, what these curves represent here are where the actual observations could pop up. So if we have our x variable, let's say this looks like it's about 22. So if our x variable is 22, we would expect the y variable to be equal to 20, but it could pop up anywhere in this under this bell-shaped curve. So it could be as high as 22, could be as low as about 18. So when we see multiple observations from people that have an x equals to 20, they're going to be scattered around in this. Most of them will be closest to 20, but they'll have a bell-shaped curve around them. And then similarly, when we go up to 25, all right, what do we expect here? It's around 21 and a half, I'd say, but yeah, we can go higher or lower in terms of that. So the data we'll see will be scattered around that true regression line with a normal distribution. So it's going to have a bell-shaped curve around that. And from this, you can see all the assumptions that we have in linear regression. Notice these normal curves, they have the same variation. So the spread is not increasing or decreasing or anything like that. The spread of those normal bell-shaped curves is staying constant for all values of x that we have. That's one of our assumptions. The fact that it is a bell-shaped curve, that's one of our assumptions. The fact that this relationship is linear, that's one of our assumptions. So let's go back to the previous slide where we list all the 4 assumptions of the linear regression, which can be very nicely put together into the line assumptions, L-I-N-E. The L stands for linearity. That means the mean of y is a linear function of x, okay? It is a straight line in terms of the relationship between y and x. So the line isn't, it's not going up and then down or anything like that. It is a linear relationship. We will talk about nonlinear relationships and how to deal with them. Okay, now I've messed up something here. There we go. Independence, that's what the I stands for. Observations don't influence each other. Now, this is something we can look at based on the data, but most of the time we have to think about the study. Okay, how did we get the data? Is there any way that one observation can be related to another observation? So it's something that we have to think about. One situation where the independence assumption fails is when we have repeated measurements. So when we have this measurements on the same person in our data set, we're not going to have that independence assumption. Okay, so that's one classic example where that's going to fail. The next letter, so L-I-N, normality. We saw this on the figure. So the residuals are normally distributed. They have that bell-shaped curve around the mean. E, equal variance. We saw this on the figure as well. So the variance of the residuals around that best line is not increasing or decreasing. We have equal variance there. Now, all these assumptions are important, of course, but there are 2 assumptions that are the most important. That's the first 2, the L and the I. The linearity and the independence are the 2 most important assumptions. And between those 2, the linearity is the most important assumption. Mild violations to normality most off. I mean, if our sample size is large enough, the normality is not going to kill us. Um, Equal variance, another one. Equal variance is more important than normality, I'd say, but it's one, again, if we have a large enough sample size, our results are going to be robust to that equal variance assumption. We'll talk about how to check all these assumptions that we have as we go on here. So if you have any questions as we go on, just throw them right there into the chat. Right. Okay, so how are we going to estimate these parameters? We don't know beta 0, we don't know beta 1. We're going to estimate these from the data. In here, when we have estimated coefficients, we'll just put a little hat on top of them. So a beta 0 hat, beta 1 hat. Sometimes you'll see people call those B0 and B1 as the estimates. And then we have our fitted line, which is beta 0 hat plus beta 1 hat times X. So this is going to be our best estimate of the mean. So you give me an X, I can plug it into that fitted line. I can multiply it by beta 1, add beta 0, and then I have my best guess for what Y is. That is going to be Y hat. That's, as I said, the best estimate for the mean of Y given X. Best guess for a new Y given X. So how do we choose beta 0 and beta 1? How do we get these two estimated quantities? Well, let's look at this little patch of data that we have. It's a simple linear regression. This is an example data. So X we have as dietary inflammatory index. This was something that was invented by James A. Baer, who's a professor here in the Department of Epidemiology and Biostatistics. The dietary inflammatory index is something you can measure from diet recall. So people give you information on their diet, goes into a top secret algorithm that Dr. A. Baer and his colleagues have developed. And what spits out is a measure of how much inflammation is in their diet. So things like red meat leads to more inflammation. Things like, I think, ginger is something that is good for your inflammation, lowers your inflammation down. So we have our single dietary measure here, DII, dietary inflammatory index. We're interested in how it's related to body mass index, BMI. We just have 15 data points. If you look at this data here, there appears to be a relationship between these two variables in that a larger value of DII seems to lead to a larger value of BMI. There's some association between these two variables. We don't know if that association is causal. We don't know if that the high DII is causing a high BMI. We're not saying that. We're just saying that the two are associated with one another. There's a few different lines here. Okay, we have the blue line, the green line, and the black line. Any one of these could be our chosen line for our linear regression. Which one should we choose, and why should we choose it? So should it be the blue? Should it be the black? Should it be the green? Now, first one I'm going to throw out is the blue line. I'm going to throw that out because you can see a lot of the data points here are below where that blue line, they're below the blue line. So we have too many data points below. We only have a couple above. So that one doesn't look to be too good, but it's a little hard to tell between the black and the black and the green line. Ooh, a little part got cut off there. So here is so what we're going to do to choose the line, we're going to use something called the least squares method. So for any particular line, we can get what we call the residuals. So we see EI here. That's going to be the difference between the fitted line and the observation. And down here, we have the difference between the fitted line and the observation. So all these points would have one of those residuals for this green line. Similarly, with the black line, we could estimate the residuals for all observations. Difference between the black line and the data point. Difference between the black line and the data point here. So for both of these lines, we could get residuals for all subjects. So for all the green subjects, we have all the residuals. For all the black subjects, we have all the residuals. What we're going to do is we're going to take all those residuals, we're going to square them, so then they're all positive, and we're going to add them up. And the line that has their sum of squared residuals, so each residual squared, added up, sum of squared residuals, the line that has the smaller sum of squared residuals, that's the one that we would prefer. So that's the line that we're going to say, well, this fits the data better. And this is called the least squares principle, often called ordinary least squares to differentiate it from weighted least squares, which is something else. So we use the ordinary least squares principle to get our best line. And that's what this guy that got cut off right here. What we do is we minimize the sum of each yi minus the fitted line, the y hat I squared, and ordinary least squares is going to pick the line that has the smallest squared residuals, sum of squared residuals, SSE. So here's another quick example. This is it's going to match the example that we'll go over in the R component here. We have age, we have systolic blood pressure. It's just a small data set here. We have different ages, different systolic blood pressure. So the first person is 38, systolic blood pressure of 116. Second person's 41, systolic blood pressure of 120. So on and so forth. We have 9 subjects. Average age is 51 years. Mean systolic blood pressure is 136.3. This is how we would run a linear regression in R using the LM command. And for this example data, we would get beta 0 hat equals 60.5. And beta 1 hat is 1.49. So the 60.5, this would be the average systolic blood pressure for someone when their X is 0. So it's our estimated average systolic blood pressure for a newborn, which is not anything we're interested in, but it's something that does come out of the model. What we'd be more interested in here is the slope, the 1.49. And what it says is that for each additional year of age is associated with a 1.49 mmHg higher average systolic blood pressure. So every time someone ages 1 year, we would expect their systolic blood pressure to increase by 1.5. If we're interested in a 10-year age difference, we would take this coefficient and multiply it by 10, which would give us 14.9, about 15. So a 10-year age difference corresponds to about a 15 mmHg difference in average systolic blood pressure. We can predict someone's average systolic blood pressure. So at age 55, we would plug 55 in there, multiply it by 1.49, add our intercept, and we get 142.5 for the average. Should we use this line to predict systolic blood pressure at age 16, at age 88? No, we shouldn't. We look at our data here. Youngest is 38, oldest is 65, and we really don't want to extrapolate beyond those ages. And even predicting at the endpoints is not going to be great. But certainly we don't want to go any further than that. So we want to stay within the range of our X variables when we are doing some prediction. Um, the next thing we'll talk about is the coefficient of determination. This is something we get. This was something we get back from our linear regression, and I laugh a little bit there, mostly because of the name, uh, coefficient of determination. Like it's such a serious sounding name, but hey, that's what it's called. I don't name these things. The interpretation of it is the total, it tells us how much of the variance in Y is explained by our linear regression model. So we split the total variation in Y into two pieces. Um, the variation explained by the fitted line plus the variation left unexplained. So this model, it explains some variation. It does not explain other variation. And that is the ratio of the variance explained to the total variation is what gives us our R squared value. A higher R squared means the line accounts for more variation in Y. So you can kind of think about it as almost like a grade on your linear regression line. So if it's like zero 0.9, you're explaining 90% of the variation. Um, and here, yeah, so if R squared is equal to 0.92, age alone accounts for 92% of the variation in systolic blood pressure in this small sample. Now that's an insane amount of variation to explain in systolic blood pressure from age. So it's just an example here, and we'll see actually in the Framingham data how much it explains. And this is our small sample of data here. And you can see that it's cherry picked to fit the data particularly well, our R squared value 0.92 here. So R squared is useful, but it's all comparative. It's just useful from a comparative standpoint. So there are some analysis. Let's say you're in physics, for example, and you're interested in the relationship between some variables. Now, the laws of physics are probably going to do most of the job. I'm telling you what the relationship between those two variables are, and you could get an R squared 0.95, 0.98, something like that. In biology, in psychology, public health, when we're talking about humans and how humans respond to things, there's a lot more variation that is going to be left unexplained. We have things like genetics, how your whole life, how healthy you are, all these things that we're not going to have great markers of in our data. So a lot of times we're not going to see R squareds that are this high, that are going to get up to the point that we see right here. So it's all comparative. Very important. R squared never decreases when you add predictors. Okay, so if we start off with we're using age to explain systolic blood pressure, and then let's say we throw in another predictor variable. For example, are you a Knicks fan? Okay, I mean, great Knicks fans, great people, as we all know, but is it related to systolic blood pressure? Well, let me think about it. No, probably not. Okay, it's probably not related to your systolic blood pressure. But if we throw that into our model, our R squared is not going to go down. So if it was 0.92 with just age, it's not going to go to 0.9 when we add a predictor. It's going to be at least 0.92. So R squared is never going to go down when we add an additional predictor. There's another measure that we're going to use called adjusted R squared. This is something that can go down when you add an additional predictor. There's some other things, AIC. So R squared in itself, we can't use it to select the best model. That's the point of this bottom part right here. Can't use it to select the best model. Adjusted R squared, AIC, formal F test, those things we can use to select the best model, but R squared by itself, we cannot. Okay. All right, so we're going to move on to inference here. So we get this value, 1.49. This is our point estimates from one sample. A different sample of 9 people, we'd get a different number. So we want to use that 1.49 to give us some idea of certainty. How certain are we about this 1.49? Is there a chance that this value is actually 3? Is there a chance this value is actually 0? So this is what we mean when we talk about inference. We want to use the data and the current value that we have to get some idea of what's going on in the real world. So there's 3 questions we can answer. How much would beta 1 vary across samples? So if we took another sample of 9, another sample of 9, how much is this 1.49 gonna vary? What's a plausible range for the true population beta 1? This is going to be answered. We're going to get something called the confidence interval, which we talked about on Friday. Is beta 1 different from 0? This is what we're going to test this using our hypothesis test. So we're going to create a test statistics that assumes beta 1 is equal to 0, and it's going to say, well, how weird was this value that we got? All of these quantities we're going to be able to get using the summary function in R, and we're not going to focus on so much on the confidence intervals, but we're really just going to focus on the interpretation. So how we get a confidence interval, we take our estimate, we add and subtract the standard error of beta 1 times this t star. And this is going to be a critical value. When we're doing a 95% confidence interval, that t star is going to be about 2, a little bit higher when the sample size is smaller. So for example, here, if we have beta 1 is equal to 1.49, standard error is 0.164, the 95% confidence interval we get is 1.1 to about 1.9. How we could interpret that is we are 95% confident that in the broader population this sample came from, the true mean increase in systolic blood pressure per 1 year increase in age is between 1.1 and 1.88 milligrams Hg. The confidence interval doesn't say that there's a 95% chance that the true slope is in that interval. The true slope is fixed. It's either in the interval or it's not. So the 95% really refers to if we did this same thing a whole bunch, if we did it 100 times and we got 9 new subjects each time, about 95 of those would actually contain the true value. Okay, one last slope before we go to our example. So lastly, we have a hypothesis test where we're interested in, is the slope actually equal to 0 or is it not equal to 0? Is there any linear association between the population? The test statistic, it's just the ratio between the estimated beta 1 and the standard error. Here you can see that ratio is equal to 9.09. P-value is less than 0.0001. So what that tells us is that if the true beta 1 was equal to 0, the chance that we saw what we saw was very, very, very low. So that would lead us to say, well, probably we'll reject the null hypothesis. We'll reject that slope is equal to 0. So here there's strong evidence that average systolic blood pressure is associated with age, and here that average systolic blood pressure increases with age. If we did not reject age 0, that doesn't prove that beta 1 is actually equal to 0. It just means that the data are consistent with beta 1 being equal to 0 given the sample size. Small sample sizes have low power. So if we only had 3 subjects, and maybe if that's the case, our p-value is not small, 0.5 or something like that. That doesn't mean beta 1 is equal to 0. It just means with the data that we had, there's no indication that it's different from 0. Okay, let's go to our example here. Okay. All right, and please, if you have any questions, you can put them in the chat, or you can just unmute and ask them. Yeah, either one of those works. Okay. Since everyone was here last week, you kind of know how these Quarto documents work. And while I'm going to have this open, I'm also going to open the actual .qmd file. So I'll give you a second to do that on your end. And then you can run these things while we're doing them. You can see them yourself. The most important thing is to run this first one to make sure that the all the packages that we need and the are going to go into the are going to be loaded in. Again, if you have your file structure the way I do here, so this .qmd file is in week 2 statistical modeling, day 6 linear regression. If it's in there, then this part should run fine, and the data should not write in. We're going to have a break in about 15 minutes. If you have some troubles in that situation, just hold off until we hit our break, and we can try to troubleshoot what's going on with you, going on with your R situation. Okay, so we have this Framingham data, which we used a lot last week. First example we're going to do is systolic blood pressure by age. The second example, we're going to use a different data set. Okay, so Framingham heart study, obviously this is a important study of cardiovascular risk factors. Here we're just going to look at age and systolic blood pressure. Whenever I'm doing a linear model, the first thing I want to do is I want to look at a scatter plot of, in this case, the two variables that I'm interested in. So I want to look at a scatter plot where age is on the x-axis and y is on the but the y variable is on the y-axis. So here, systolic blood pressure is going to be on the y-axis. There's so many things this is going to do for me, just this scatter plot. It's going to help me out in so many ways when I'm going to fit my model later on. So this is something that we always want to do. So all this is just this code right here. This is just a scatter plot. Okay, just doing a scatter plot between age, systolic blood pressure. I'm adding some things to it. So we worked on this on Thursday. I'm adding a smooth lowest line. This line can look linear, it can look non-linear. So it's just a little indication of what the relationship between these two variables are. Is it linear? Is it non-linear? And the rest of this is just window dressing to make this look pretty. So we saw this curve last week, and what I told you last week is you won't find many scatter plots that have a more linear relationship than these two variables right here. You can see the relationship between age and systolic blood pressure as I would say remarkably linear in this case. Maybe a little tapering off down the end here. Probably not even there. That's probably a selection bias issue, I would say, if anything. But this is a remarkably linear relationship. What that tells us is that when we fit a regression model between age and systolic blood pressure, we can just put age into the model. We don't have to do anything to it. We don't have to, we'll talk about nonlinearities later. We don't have to do any fancy transformations, any logs, any squares, we don't have to do any of that. Just put age in the model. Very, very nice to have that. I'm going to come back to this section 2.3 in a little bit. Okay, so to fit the simple linear regression model that we see right here, I'm going to use the LM function in R. And what we're doing here is we're using this tilde part right here. This is giving R what the formula for the linear regression line. The SYSBP, that's our y variable. And then we're going to use tilde, going to give it our x variables. Excuse me. So here we only have one x variable, age. Now there's also an intercept in this function. We don't have to tell it the intercept. Okay, so it assumes that an intercept is going to be in the model. If you don't want an intercept in the model, you would add 0 plus age. And that would tell R, okay, forget the intercept, just have age in the model, but we're not going to do it. We usually want an intercept in here. And then we use the summary function to get the meat of the information about the linear regression model that we just ran. So we run this, we get an intercept of 82.1. So what this tells us, this is the estimated mean systolic blood pressure for a participant that is aged 0. So not really meaningful in this situation because we don't have anyone that's even close to 0 in our data, right? So we wouldn't want to interpret that. We wouldn't want to really use that in any way. Then we have our coefficient for age, 1.01, very, very close to 1, which is nice for interpretation here. So how we would interpret it, so for each additional year of age, systolic blood pressure is estimated to increase by 1.01 mmHg on average, holding all else constant. So we get, all right, for each additional year, systolic blood pressure increases by about 1 unit. If you're talking about a 10-year age difference, which is a little more interpretable, there you're going to see about a 10-unit increase in systolic blood pressure. That's what we would expect it to be. Okay, what else do we have on here? We have the R squared value that we see right here, 0.155. So 15.5% of the variance in systolic blood pressure is explained by age. So you may think that's a low value. We're not going to see anything higher than that. So that's just how much variance age explains. There's a lot of other factors. There's genetics, there's diet, there's exercise, there's a million things that we're not putting into this model. Just age explains 15%. The association between them explains 15%. So we shouldn't try to get it any higher than that. That's really what it should be here. P-value. So p-value is very, very low. So there's clearly seems to be a relationship between age and systolic blood pressure between these two. If we want confidence intervals, okay, so let's look at this right here. So we ran this model. We ran this LM. So we said LM SYSBP tilde age data equals Framingham. And we stored that as an object called SYS underscore, SBP underscore model. So this is our systolic blood pressure model. This SBP underscore model, this has a lot of information to it. We take that's what we give to the summary. We say summary of this model tells us all the information. Something else we can do, we can use this conf int of the model. That will give us confidence intervals for the parameters that we get from the particular model. By default, it gives a 95% confidence interval. We can tell that because we have the 2.5 here and the 97.5. So we're 95% confident that the true slope for age is at least 0.94 and at most 1.08 here. So that's nice. We can get our confidence intervals right for that. By default, it's going to give us a 95% confidence interval, but we could get other confidence intervals for that. Let's take a look. So I'm going to run down here. I'm going to run the model here. It's linear regression model. Run this confidence interval part. Use question mark conf int to see what the argument is. So level. This is what we would use if we want to not give a 95% confidence interval, but something else. If I say level equals 0.99, this would give me a 99% confidence interval. And we see that the 99% confidence interval is going to be wider than the 95%. I could say 0.9 to give me a 90% confidence interval, and that's going to be more narrow than the 95% confidence interval. So we could get anything we want. Plotting the regression line, this is going to be very similar to the code we used for the previously. So the only thing different is instead of method equals lowest, here I'm going to say method equals LM. That is literally the only difference between these two codes. And that's going to show us what our linear regression line looks like here in terms of the data. There is there is a shaded band here, which is a 95% confidence interval for the mean, but it's so skinny that you can barely see it towards the end here. So the 95% confidence interval for the mean is very tight around the actual fitted line. So what is the 95% confidence interval for the mean? So what that says is for a given value of x, where is the actual mean of y? So if we look at this, for an age equal to 50, we could plug this in and figure it out, but our predicted mean, what's that? Maybe 133 or so is going to be our predicted mean. So for individuals in the Framingham Heart Study that are 50 years old, our predicted mean is maybe 133 mmHg. We want a confidence interval for that. Okay, that tells us, all right, we're 95% confident that the true mean is within these particular bounds. Bounds that we would get, and maybe we get something like we see down here. A prediction interval is different. Okay, prediction interval is different. A prediction interval gives us an interval where we should see 95% of the observations. It's very different than a confidence interval. So at age 50, the confidence interval is very tight around that predictive value. Prediction interval is going to be very wide because you can see that individuals can have systolic blood pressure maybe as high as 200 and even below 100. So that's what a prediction interval is going to tell us. It's going to tell us where the actual data are going to fall for this particular value of x. It's going to be much wider than the confidence interval is. So in this example, 50-year-olds, predicted value is 135. Confidence interval is pretty tight around there. Prediction interval is going to be much wider than the confidence interval will be. So going to use these for different things. The confidence interval tells us, all right, what's the mean value for that particular value of x? The prediction interval is going to tell us, all right, somebody new's walking in the door, they're 50 years old. Where do I think their values can land? What values am I going to say, all right, that's a wacky value. Something is going weird there. So they answer very different questions. One has to incorporate individual to individual variability. The other one doesn't. It's just talking about the average for that particular x value. Okay, good. Okay. Next thing I want to talk about is the ANOVA table. ANOVA table is something that we can get from our using, scroll down here. using the ANOVA function. I see we get all this stuff that we have in this table right here. The ANOVA table is really going to break down the different sources of variation for the entire model. So this SS reg, that's going to tell us how much of the error is explained by the regression model. SS error is going to be the remaining, how much is going to be the error. SS total is going to be the total variation in the outcome. So it splits the total variation in the outcome into how much is explained by our regression model and how much is left over in the error term. And the ratio here is going to give us that coefficient of determination, the ratio of the SS reg to the SS total. The MS error, this is going to give us our estimate of the residual variability. So when we did our summary, sorry, I'm flipping around so much between things here. This is available to us right here. So this gives us how much the standard deviation of the residuals. We see it's about 20. So that tells us that for any particular estimate of the regression line, about 68% of people are going to be within 20 units of that estimate, and about 95% of people are going to be within so within 40. 68% of people will be between 20, 95% of people will be within 40 units of that particular regression line. So that's something that comes out of our ANOVA table. Also, usually over here, the last part, it'll have a p-value with the ANOVA table. And you can see that in that ANOVA table that I showed you down here. So it gives you this p-value. What this p-value, one of my old teachers, they used to call this the shotgun test. And it really tells you, is anything in your model worth a darn? Do you have any predictors in your model that are explaining anything in the outcome? And so he used to always tell us that's the first thing you look at when you do a linear regression. So you fit a linear regression, you look at that shotgun test first. That is almost always significant. If that's not significant, I mean, you just kind of have to throw up your hands. Now, when we're doing simple linear regression, this shotgun test is going to be the same as the t-test for beta 1, and it's also going to be the same as a correlation test. So when we only have one variable in the model, all three of those tests are going to be the same thing. They're going to have the same significance. When we get to models that have multiple components to them, then those tests start to split apart, and that's what we'll talk about in the next section. When these come apart, when we have different variables in the model. And again, the summary LM object, it's going to report all this. Let's go back up to that summary. This right here is going to be our overall F-test. And again, we have excuse me, we have our variance here. So the summary is basically going to give us all of us. So I don't usually look at the ANOVA object very much. The summary gives us the R squared. It gives us our shotgun F test. It gives us the variance, and that's really what we're interested in. So what can we do with a simple linear regression? There's a few things. We can fit a regression line to describe the average relationship between X and Y. When we did this in the Framingham, we found that every time someone ages a year, we would expect that their systolic blood pressure would increase by 1 point. We have R squared, very useful measure, gives us an idea of how closely related these two are, how much of the outcome is explained by a linear relationship with our X variable. We get a test. Are these two related? We see that it does appear that age is related to our systolic blood pressure. We get confidence intervals for the the mean at any particular X value. Prediction intervals is something else we can get. So confounding is something that's very important when we want to make causal statements. So let's suppose we're doing a model between stress level and the severity of muscle cramps. We do this, we reject H0, we see that there's an association between stress level and the severity of muscle cramps. What else could explain the association between these two variables? Well, first off, could be reverse causality, that it's not actually stress level impacting muscle cramps, it's muscle cramps causing stress. That's something that could be certainly present. A confounder, poor sleep, could be related to both of these two. And it's not actually that stress is related to muscle cramps, it's that poor sleep is impacting both of those. If we don't have sleep in our model, we can't determine that. Selection, only people with stress, high stress and muscle cramps ended up being in our study. So that's a selection bias that could actually cause this relationship to appear. Simple linear regression, we can't really differentiate these things. Multiple linear regression is going to help us differentiate measured confounders. So if we had a measure of sleep, we could put that into our model, and that will tell us, hey, then we can adjust for the impact of poor sleep. Reverse causation, we have to work really with the study design to do that, to get some ordering between those two. Selection, again, that's something that's more on the study design part. But when we come back, we'll try to address that first part, that confounding with measured confounders. We'll talk about multiple linear regression, where we'll bring some other variables into the model and see if we can get some information about that. Okay, so I have 11:03 right now. Why don't we come back here at 11:15 and we'll start talking about the multiple linear regression model at that point. Great. I'll see you in a few minutes. If you are having issues getting your data in, stay on and unmute yourself. You can share your screen and we can try to troubleshoot any issues you're having. Great. Get started. We'll get started here. I will share my screen and we'll get back to start where we left off. Okay, so we did our simple linear regression. Now we'll move on to multiple linear regression. You may have noticed I changed my scenery here. We didn't have anybody in the lab, so I just came over to my office, my home turf, a little more comfortable here. If any of you want to come in person, just let me know. I'm happy to go back to the lab, but if nobody's here, I'll probably stay in my office. Okay, so multiple linear regression. So this is an extension of simple linear regression when we have multiple predictors. Interpretations are going to be a little bit different. So interpretation of beta j is going to be the expected change in y for a 1 unit increase in xj, holding the other predictors constant. So that's the real change here between the simple and multiple linear regression. Is the interpretation is, all right, so we're changing age, holding everything else in the model constant when we have that in there. And this is what helps us with the confounder part of this. So for example, maybe poor sleep is related to both stress and cramps in this example. But when we have multiple linear regression, if we have sleep in the model, our interpretation for the stress coefficient is going to be the association between stress and cramps holding sleep constant. So it's like we're comparing two individuals that have the same value for sleep, they have a 1 unit difference in the stress variable. What's the relationship here? So this is going to help us address this confounder part of the regression issue that we had, multiple linear regression well. Now, again, as I said before, there's two separate uses of regression. First one, inference, to get an unbiased estimate of a particular coefficient. For example, previous thing we were talking about, we really want to know how stress level is related to the severity of muscle cramps. We're very interested in that particular coefficient. So this multiple linear regression model is going to help us out because we're going to be able to adjust for other confounders. Confounders, I mean things that could be related to our exposure of interest and the outcome. The second one is prediction. When we're doing prediction, we're not so much interested in one particular covariate. We're really interested in getting a good predicted value of our outcome. As I said, in public health, and in a lot of sciences and psychology, we're more interested on the inference side. We're more interested in we have one exposure of interest. We want to know, is there a relationship between these two variables? But sometimes we do have prediction. Trick question is, let's say y equals beta 0 plus beta 1 x1 plus beta 2 x1 squared plus epsilon. Is that a simple linear regression or is that a multiple linear regression, and why? Tough question. Well, kind of seems like a simple linear regression because we only have one predictor variable, x1. It's the only thing we have measured. So we're only getting the relationship between x1 and y. Kind of seems like a multiple linear regression model because we have beta 2 here. We don't just have beta 0 plus beta 1. Which one wins out? Turns out that this is, in fact, a multiple linear regression model, even though we have the same variable x1 and x1 squared. Why is that? Well, some of the issues in multiple linear regression that we'll talk about, one of them is there going to be large relationships between the explanatory variables? That doesn't happen in simple linear regression, only multiple linear regression. And that is going to be an issue that we may be interested in right here. That's called collinearity. So issues like collinearity come up in this particular model. How we estimate the coefficients, more on the lines of multiple linear regression. So even though we only have one predictor here, this is actually considered a multiple linear regression model. Just a quick quiz for you there. The example we're going to do in R is a situation where we have an outcome variable, VO2 max, maximal oxygen uptake in ml per kg per minute. It's a standard measure of aerobic fitness. I've heard it described as a measure of sort of the engine that you have. So if you think about an athlete or like a car, VO2 max is a measure of the power of the engine that you have. And some folks are very pro on VO2 max as an overall measure of health, overall measure of aerobic fitness for sure. It's very hard to measure though, VO2 max. It has to be measured in a lab with a mask. If you have a watch, it will give you a measure of VO2 max sometimes, but those measures are not very good. To get a good measure of VO2 max, you have to have something like a mask on you that really measures how much oxygen you're taking in, how much oxygen you're putting out. That is what's going to be the gold standard measurement. So we aren't always able to get that gold standard measurement. So how could we predict it? So this is a situation where we're not interested in one of these variables in particular. We're interested in getting a good predictive value of VO2 max. This could be something that, for example, Garmin may be interested in. Hey, can we use some variables, some easier variables to get, like what we have down here, to estimate VO2 max, and then give it to our people that have the watch. So some of the predictors, some of the data that we have, a runtime for 1.5 miles. Okay, how fast can this person run 1.5 miles? Age, weight in kilograms, resting heart rate, running heart rate. So that would be an average heart rate while somebody runs, and maximum heart rate. So we have three different heart rate measures because heart rate is something we can measure on our wrists using accelerometry pretty easily. So these are all things that we could measure on, say, a Garmin watch, and we're interested in using this to predict the value of VO2 max. So before I fit the model, we always kind of want to think of what should happen here. What direction should each of these beta coefficients go? First off, faster runtime should mean higher VO2 max. So faster you can run, so lower the runtime is, the bigger your engine is going to be. So there should be a negative slope between runtime and VO2 max. Older age, sadly, usually means a lower VO2 max. Negative slope, you get older, that engine is not quite as powerful. Heavier weight tends to also mean lower VO2 max. And lastly, lower resting heart rate is a sign of fitness. So people that are very good endurance athletes, for example, they can get very low resting heart rates. I have a friend whose resting heart rate is in the high 30s. I mean, it's incredible. So because they have very strong heart. If a fitted coefficient has an unexpected sign, it's a red flag that is worth investigating. Often points to collinearity, which we'll talk about on the next slide. But let's go over to our example here. So this is in section 3. So if you just click on the 3 here, it'll take you down to that. And I also have this open in our studio. So we can see, you can go down to this part, click that arrow, and this data is just all on here, so we don't have to read it in or anything, but we have a nice data set here. These are all numeric variables that we'll be looking at. All right, so reading this in using the glimpse functions, one we haven't used yet, but it's similar to the str that we use. Tells us something about our variables here. These are all numeric variables. Nothing here that's categorical, that should be categorical or anything like that. So we're just going to keep everything as continuous. The first thing, similar to before, I want to check the variable form for each predictor. This is always the first thing I want to do. I want to look at a scatter plot of the data, similar to what we did with age and systolic blood pressure. This is going to give me a lot of information. I'll just scroll back up to that previous one that we looked at. Yeah, so this is the one we looked at it with age and systolic blood pressure. Told us, hey, a linear relationship is a good thing to use here. It seems very linear. Also, we could see outliers right away. We could see some of the values that are different from everything else. Scatter plot gives us that as well. So scatter plots are always a great thing to start off with. Okay, so let's look at our scatter plots here. As I said, the Framingham, the systolic blood pressure and age example is going to be the most linear relationship you ever see. So these are things that this is kind of more what I'm used to seeing when I look at plots like this. So we have this lowest smoother here, which can give us, as we can see, nonlinear associations. But what I want to use this for is to take a look at the data and see, all right, what are some relationships that we could possibly use here? So here we have the relationship between age, and we have our outcome VO2 max on the y-axis. Relatively linear association here, and it appears that older age is associated with a lower VO2 max, which is what we thought it would be. Going to the right, max pulse here looks relatively linear for most of it, some wiggles in the middle, and then kind of goes off a cliff at the end. Now, we want to discount this last part where it goes off a cliff because it's really just one observation that is bringing this mean line way down there. If that observation was not there, if you could almost just black off this last, or just put a black box around this last part, things would probably look relatively linear here. What we see is that people with a higher max pulse have a lower VO2 max. Now, I didn't have any hypothesized relationship between these two in the notes because I wasn't sure, but it appears that's what we look at. Resting pulse. So for the most of this, again, lower resting pulse, higher VO2 max, and it tends to go down, but then it is sort of creeping up at the end. Now, this is the one out of all of these, I would say, that looks the most nonlinear, that there does appear to be some maybe U-shaped relationships there. So we could think of a squared term here. But also it could be that there's just not a strong relationship between these two variables, and what we're seeing is just random variation. Running pulse, again, relatively linear, and a higher running pulse. We see a lower VO2 max. This one is very similar to max pulse. And this is one thing we have to remember. When we're looking at the relationship between max pulse, we could see some relationship here, but it's actually maybe running pulse that is the one that matters. Could be that max pulse doesn't matter at all. The thing is that max pulse and running pulse are going to themselves are going to be related to one another. So a higher max pulse is also going to mean a higher running pulse. So it's kind of hard to determine when we have these relationships that are these variables that are going to be so strongly related. Runtime here, clear relationship. Okay. When we have a longer runtime, we have a lower VO2 max. Relatively linear relationship, maybe some curvy linear towards the end here. Here we are going to use a linear relationship to represent that. And then weight, this is one roughly linear, may not be any relationship here at all. It looks relatively flat. It's not really going up or down, so it's hard for us to tell. Some summaries here. Runtime, certainly the strongest negative linear relationship. Age, weight, run pulse, max pulse, roughly linear. It's going to be some more scatter. They're not as strong. Resting pulse. I would add weight. Resting pulse and weights are kind of the two that those two don't appear. They may be related. They may not be related. Okay, let's go back to our notes. And again, if anything I'm saying is unclear, please speak up or write something in the chat. I do have a tendency to start to talk fast when I'm not getting any questions. So if you have a question, speak up, put it in the chat, whatever you're comfortable with. I'm sure somebody else probably has that same question. So we'll talk about some of the assumptions here. These are going to be the same that we had in the simple linear regression model. We'll talk about these in more detail later on in the notes. But linearity, independence, normality, equal variance, those line assumptions. One additional concern in multiple linear regression is collinearity. This is what happens when two variables are very closely related to one another. Um, Perfect collinearity, this is when one variable, or say there's three variables that perfectly explain one of the other covariates. When that occurs, you're going to get an error. Your model is not going to be able to fit. More um, more likely is imperfect collinearity. This is when we have some variables that are highly related to one another. Let me get my little note thing out here. I'll do that, yeah. So this is our what's going to happen when we have variables that are highly related to one another. This is more common and it's going to cause some issues. So here, this is something that could occur. Um, uh, the variables that I would think that would be the most highly related to one another are max pulse and run pulse. So there's going to be a high correlation between those two. We could actually even look at this using the data here. But let's do that because I'm curious. I did not look at that before. So I've run the data here and I'm interested in what's the relationship between run pulse and max pulse. So a few different ways I can look at this. I could plot these two variables. Um, let's I'm going to put this up here. So I could say ggplot. The data here is called fitness in all caps. AES, which is our adding our aesthetics, our X variable. Doesn't matter which one I do, but let's look at run pulse. Excuse me, X equals run pulse. Y equals max pulse. Plus, I'm just going to do this very simple, just genome point. Open and close. And I'm going to run this. Okay, so there we see a very simple scatter plot of max pulse and run pulse. Clearly, a strong linear relationship between these two. So this is going to make it difficult for us to determine the relationship of run pulse and max pulse at the same time. Why is that? Well, let's go back to the let's go back to our interpretation. So if we have run pulse and max pulse in our model, so the coefficient for run pulse, for example, is the expected change in VO2 max for a 1 unit increase in run pulse, holding other predictors constant. So holding some of those other predictors, one of them is max pulse. Well, turns out it is difficult to change run pulse while holding max pulse constant. That's what we see in this figure here. Usually, if run pulse is going to increase by 1, there's going to be an increase in max pulse. This is called collinearity, something that can give us issues in our multiple linear regression model, and we'll take a look at it in the when we fit this model here. So in MLR, we have the same line assumptions, but we also have this collinearity issue. When we have X variables that are highly related to one another, we're going to get some strange things that can happen. Signs can flip when a correlated predictor is added or removed. So we'll look at some diagnostics with this as we go on. Okay, so how do we estimate our coefficients? We're going to use the same least squares method that we did previously. So for any line, we can estimate the residuals, square them, add them up. We want to get the line that has the smallest sum of squared residuals. There's a closed form for this using linear algebra. Excuse me. Each of our beta coefficients that we get, it's going to have a standard error. in it. We'll see that when we use the summary object. And again, interpretation, beta hat j depends on which other variables are going to be in our model. When we have a different model, we're going to get different beta hat j's. All right, so let's go to our example here. I'll just go to the full model. So the first model that we're going to fit, we're going to have all 6 predictors in there. So we're going to explain this VO2 max with age, weight, runtime, resting pulse, run pulse, max pulse. So I use the data equals fitness objects, summary of the full model here. So we have our coefficients, our intercept here. This is going to be the predictive value when all these x variables are equal to 0. It's not going to be meaningful here because that would be an age of 0 and a weight of 0. But here we have our all of our regression coefficients. We have our p-values, which are an indication that if we assume one of these, if we assume runtime is 0, how weird was the data? So runtime is the strongest predictor by far, highly significant, has a large coefficient relative to its the scale of it. Weight and resting pulse. These do not appear to be related, weight and resting pulse. We can judge that by the relatively high p-values. Run pulse and max pulse are correlated, so including both may cause redundancy. This is multicollinearity. So what we see here is that run pulse has a negative relationship, so higher running pulse, lower VO2 max. Max pulse has a positive relationship, higher max pulse, higher VO2 max. If we look at the figures here, max pulse appeared to have if anything, a negative relationship. Run pulse also appeared to have a negative relationship. Why are we getting different signs here? Well, when you have different signs like this is a sign of collinearity causing some issues with your linear regression model. So the fact that we're getting a positive and a negative sign here, what I would think, they're actually not positive and negative. It's just that the strong relationship between these two variables is causing some issues in our model, like a positive and negative relationship. There was a example I remember going over in when I was a student where we were trying to predict how far NFL punters kicked the ball, and we used their left leg strength and their right leg strength. Now, left and right leg strength are highly related, and when we put them in the model, left leg strength had a positive relationship, right leg strength had a negative relationship. Is that actually the case? No, it's not actually the case. It's just collinearity, just the relationship between these two variables that's causing some issues here. So what could we do? Well, we could add another variable, which is maybe the average of run pulse and max pulse, so that we get both of those measures in there. We could just remove one of them, say these are too highly related. We can't differentiate the relationship between these two. Those are kind of the two major ways that I would look to address this. But that's our fitted multiple linear regression model that we have there. Okay, so before reporting any inference, what we want to do is we want to check whether these line assumptions are going to be plausible. Most of the plots we are going to look at are residual plots. So these are going to be a look at the difference between the observed and predicted values. And we're going to use these to determine whether our linear regression model seems to be good or not. Getting these in R is very easy. We just say plot, and then we give it that model object. We're first going to check this for our first regression model, where we have age and systolic blood pressure. Then we'll come back and check it for our multiple regression model. Okay, so LINE. Let's talk about each of these assumptions. The first one is linearity. The first way to check this, you already did it. It's a scatter plot. Look at a scatter plot of the X versus Y variable with a lowest smoother. To me, this is the best way to do this. Does it look roughly linear? Another thing we can do, we can look at the residuals versus the fitted values. This is something that we're going to look at when we check the diagnostics. When this fails, we can add a polynomial term. So age and age squared, for example. We could transform y using log or square root. We can add interaction terms. So when this assumption fails, the issue usually is we want to put more variables into our model or change the variables in our model to some different form. So let's look at this. Let's go back to our systolic blood pressure and age example. And as I said, this is the most linear relationship you will ever find. There's not any issues with linearity in this particular data. We can tell that from the scatter plot. Let's take a look at the model diagnostics. So here we take this, we say plot, and then we give it the linear regression model object, and we get 4 plots back. This first one is the first one we'd want to check out for the linearity. Do we see any patterns in this plot that would indicate we need something else in our model? Here, there's a little bit of a trend that the residuals are a little bit on the low side, more negative towards the end. We did see that in the plot, that maybe things are just tapering off a little bit towards the end here, that the relationship is linear, but then maybe it's just creeping off somewhat after we get to about 65 or so. And we're seeing that a little bit in this first plot. So that's an indication that we probably could add a squared term to this model, and it probably would fit a little bit better. But here, I probably wouldn't do that. I don't think this is a huge violation or anything. So L, that's our first assumption, scatter plots, plot of residuals versus fitted values. Normality. So the residuals are normally distributed. That's one of the assumptions. That's the N assumption. We can check this through a normal QQ plot of the residuals. That's something that we see right here. So when we look at this QQ plot, showed us right here, what we want to see is a straight line. Okay, so it should go a straight line all the way to the end. All the way to the end. This one does not, it's not a straight line all the way to the end. So what we see is that there are some residuals that are much larger than they should be if they were actually normally distributed. So we see some values that are way higher. Subject 482, their standardized residual is about 7, when if it was normally distributed, it would be about like 2.5 or 3. So we're getting some large residuals, and this, you can see this on the figure here, that there probably isn't a bell-shaped curve around the mean line. It's probably has some right skewness to it. So it actually definitely has some right skewness to it. So it's a little bit skewed. So the normality here is a little bit questionable. We definitely have a large sample here. mild departures are really not going to matter, I would put this under that case. I would say this is larger than a mild difference. So maybe I would try fitting a different model, but because we have such a large sample size, it's not going to matter quite as much. If I were to change things here, what I would do is I would transform Y, transform the systolic blood pressure measurement using a log. So I would model the log of Y versus modeling just the standard Y. That's kind of the best way to usually address this. Equal variance. So for the equal variance, this is something that, again, we can look at the residuals versus the fitted values. And what we want to see here in this plot is that the variance is not increasing or decreasing. So here, again, this is an assumption that is probably violated with this data. As the fitted values are getting larger, the variability is increasing. So we're seeing more variability down here on the right side than we are down here on the left side. So when the fitted value is, say, 120, the variance from that predicted value is smaller than when the fitted value is, say, 145. We see a lot more variability here. So this is a situation we probably have a violation of the equal variance. What to do here? Again, a transform of Y, probably a log transform. So that could be a smart thing to do for this particular model to make sure we get the same inferences that we did when we started this. Let's go down to our second example, and let's look at the diagnostics here for that full model. That's down here, 3.7. So this ends up being on the final model. The QQ plot looks a little better in this situation. Some of the residuals a little bit too high, some a little too low, but not too bad. We see some kind of strange pattern here with the residuals where they appear to be going down and then going up. Is that just that there's not many values here in this when the fitted value is, say, 51 or so? Or is it something actually there? It's kind of hard to say in this situation. So it could be either one. Overall, based on these plots, there probably is some nonlinear relationships with some of these particular variables. So that could be something that we want to explore. We're not going to get a chance to talk about this in the morning here, but we'll show some ways of looking at nonlinear relationships. Okay, so it's just a summary of the different diagnostics. Another thing that is interesting to look at are outliers, leverage points, and influential points. So here, again, we have systolic blood pressure and age to demonstrate this. Outliers are values where the Y variable is different based on the X variable. So this point right here is going to be an outlier because at age 25, in this data set at least, the systolic blood pressure of 100 is very different. That's an outlier. Here we have another outlier. At age 50, the systolic blood pressure of 95 is much lower than it is based on the linear trend. A leverage point, that's somebody whose X data is strange, not their Y data, their X data. So this person right here, they're not an outlier because the trend, if we follow this trend up, this is about where we'd expect it to be, but they are a leverage point because their age is 50 and everyone else in the study is between 20 and 30. The last one we have is an outlier and a leverage point. So any of these combinations can have a large influence on a linear regression model. So this is one thing about linear regression. It's going to be sensitive to outliers and leverage points. So This person in particular, just one person can have a large influence on our linear regression slope that we end up finding at the end. Some of the things that we'll use to diagnose outliers and leverage points, one is Cook's distance. This is going to blend both of these things together, outliers and leverage points. We're going to plot this, and we're going to look for points that clearly stand apart from everybody else. We're not going to use any formulas for like cutoffs or anything like that. We really just want to look for points that are, oh, wow, that's really out there. A large Cook distance, it flags a point for some follow-up. It doesn't mean that we should automatically remove it, but it notes it to us like, hey, there's something going on here. Let's take a look at it. So we can look, hey, is this a data entry? Is it measurement error? Can we fix it? Is it a legitimate but extreme observation? Okay, that's just something we could report the results with or without it, let the reader judge. Is it from a population subgroup that your model doesn't account for? Okay, so is this somebody that, hey, our model just doesn't work well for this type of people? Okay, we can consider adding an interaction term, something like that. So let's look at this for let's go to the systolic blood pressure example first. Okay, so here's some code where we're getting the Cook's distance for every observation in our study. You can see the code to do that. And then we're going to plot these Cook's distance by the observation number. And you can see what they look like right here. So we do have somebody here that, they have a particularly large influence on our regression line, the simple linear regression of systolic blood pressure and age. Let's take a look at this particular person. So I'm taking the Framingham data set and I'm saying which dot max of Cook's distance. So I'm getting the maximum value and saying, hey, show me age and systolic blood pressure for this person. So this person is 64 years old and they have a systolic blood pressure of 295. So the age is not particularly strange. It's on the higher side, but it's not the largest. The 295 is really why this person is standing out. That is clearly the largest value. Let's go back to the scatter plot. We can see this individual right away, right here. Systolic blood pressure of 295. We don't have anyone else that's above 250. And this is a large sample. So this is somebody that's really having systolic blood pressure that is very, very high. I am not a doctor, so I can't tell you if is that an error? I don't know. It possibly could be an error, but it may not be. Could be a legitimate value as well. Let's take a look at the fitness data set. Scroll down here past the model diagnostics to the Cook's distance. So we get this for our final model right away. It's a much smaller data set. We can take a look at the observation 10, which has the largest value. And here is a summary of the fitness data set. So age 38, right away, we can tell this is the youngest person in the data set. So that's going to give them some influence. Their weight, nothing strange about that. Runtime is on the low side. Resting pulse, the low side, but not crazy. Run pulse 170. Okay, that's pretty much right at the median. Max pulse 186. That is on the high side. And then their Y is going to be the largest observation that we have here. So really nothing wrong with this person. They're just, they're just a little strange in terms of the makeup that we get for this particular person. This is the person that's person 10. We can see that they have the largest residual. Their residual is positive. That means that their VO2 max is higher than we think based on the rest of the data. So this could be a number of reasons why that is the case. So Cook's distance is a good way to get some additional information about our data, and we've accounted for variation from our predictor variables, and then we are going to get some idea of who's a little strange in this particular data set. Okay, so I'm going to stop there. We're going to break for lunch. We'll come back at 1 to do the lab, and we're going to fit some linear regression models and look at some diagnostics for some of our example data. So have a good lunch. If you have any questions, I'll stay on here for about 5 minutes or so. You can ask those. If you're having any issues, let me know. If not, I will see you back here at 1 p.m. and have a nice lunch. Welcome back, everybody. Welcome back, everybody, to the PM section. I'll do a little introduction to the lab we're going to do here, and then I'll hand it over to you to get started. Myself, Yanan, Elena will be here as you're doing the lab. You can put any questions in the chat, and if you need to, we can have you share your screen, and we can try to walk you through things. So to start, I'm going to share my screen here. So the main topics that we went over in the morning were how to fit a simple linear regression model, how to fit a multiple linear regression model, how to check the line assumptions, the diagnostics, how to look for influential measures. There were some things on this example about comparing different models. We did not go over any of that. We're going to push all that to tomorrow's class and lab. So we'll just go over the exercises we're going to focus on are just going to be on the topics that we went over for the morning section. So this example 1, systolic blood pressure and age, we really went over all of this except for this part where we were comparing 2 different ways to put age in the model. But we went over really everything except for section 2.3 in this first part. For the second example, we certainly went over section 3.1 and section 3.2 and section 3.3. Those will all be critical to question exercise 4 that you're going to do. We did not go over section 3.4 or 3.5. We did go over 3.7 and 3.8. So those are the ones you're going to want to focus on when going back to the morning lab portion, excuse me, the morning exercises. Those sections are the ones that to focus on. We're again going to use our the Framingham data here. See an example here with BMI and total cholesterol. This is a situation where we do not see a linear relationship between these 2 variables. So maybe we would want to put BMI in a different form, possibly including some other things. None of the questions are going to go over that type of stuff, but it's just a basic example here, plotting linear regression, looking at the diagnostics, so on and so forth. So you can use that. The exercises we're going to do. So first, focus on the steps, the instructions. So creating a new Quarto document. some material here to start things off with. Exercise 1 is going to simple linear regression. This time, instead of systolic blood pressure, we're going to use diastolic blood pressure. But we're going to go through things the same way we went through the first example in the morning, plotting the two variables, fitting a simple linear regression model, interpreting the slope, question about the R square value, comparing it to what we found in the morning, and then plotting the fitted regression line. Exercise 2, again, same model, still looking at age and diastolic blood pressure. We're going to look at the diagnostic plots this time. Do you see any model assumptions that are violated? And do Cook's distance and getting some confidence intervals for the regression coefficients. We're going to skip exercise 3. This is a one that we're going to compare models. We'll talk about that next tomorrow. But then you are going to do exercise 4. This is going to be a multiple linear regression model. Systolic blood pressure is going to be the outcome. We're going to plot this. This plot is going to go similar to the plot that is created right here from the fitness data set, so that this code is going to be useful for you, just changing it to match the example that we're doing here. And hey, which variables seem to have a linear relationship, any obvious nonlinear relationships, and then just looking at some of the missing values in terms of these variables. Check how many of these variables have missing values, and that's going to have some impact on our model because those individuals are not going to be included in any of the model fitting. And then we can stop right there. So good luck on everything, and please let me know if you have any questions or if anything comes up.